Hello, welcome back to the video course on fluid mechanics. The last lecture we were discussing about the drag and lift forces coming on the immersed bodies in fluids. So, we have seen the expression for the drag force and the lift force and various situations where the drag and lift acts on the say bodies and then how it can be calculated. Also, we have seen that depending upon the shape of the body, depending upon the profile of the body and then how we place it, just like in the case of airfoil, we have seen the drag changes and also the lift forces changes. So, and also we have seen the mainly we have the pressure drag and the friction drag with respect to the viscous effects of the fluid. So, now say before further discussing on the say various how to find out the drag coefficient for laminar turbulence with respect to the boundary layers, we will just to see how we can first initially we will discuss how this we can reduce the drag effects on bodies, either moving bodies or stationary bodies in fluid. So, the topic first the topic which we are going to discuss is reduction measures of pressure and friction drag. So, here you can see in this slide, here we have an aircraft and then while it is flying you can see that various forces acting are the drag in this direction and then there will be a thrust in this direction and then the weight of the aircraft and then lift. So, as we have already discussed, the drag is a mechanical force generated by a solid object moving through a fluid as in the case of an aircraft. So, say the main drag effects are here the pressure drag and friction drag. So, what are the various possibilities depending upon the say whether it is blunt body or it is the streamlined body or depending upon the shape of the body and profile, the drag effect will be different. So, the how we can reduce this pressure and friction drag. So, that is what we want to discuss here. So, as I mentioned earlier, so if we consider an airfoil as in this slide. So, the airfoil is placed just within the say if the free stream flow is coming like this and the airfoil is placed in the direction of the free stream, then we can see that the drag effect due to the pressure drag effect will be much lower and only friction drag will be there. So, but when we slightly say tilt the airfoil in such a way that say for example, if the angle of attack is 5% as in this figure, then you can see that the drag effect say the friction drag effect say compared to the pressure drag will be more. So, here depending upon the angle of attack, the second figure again the angle of attack is 40 degree. So, that you can see that again the flow phenomena surrounding the airfoil is changing. So, what we can observe here with respect to this slide is that, so depending upon the placement or the location or the how the profile of the body which is immersed in the fluid flow. So, then accordingly the drag effect whether it is pressure drag or the friction drag it changes, its nature changes. So, we say the question here is how we can reduce the pressure and friction drag depending upon the shape or whether depending upon the placement of this say as in the case of this airfoil. So, now the pressure drag we have seen the drag is concerned either it can be mainly it can be pressure drag or the friction drag. So, the pressure drag can be reduced. So, various two important steps which we can use it here is making the body as streamlined. So, the pressure drag effect can be reduced by making the body as streamlined, and the second possibility is that we can reduce the length of the components where applicable. Say example the wingspan of an aircraft. So, you can see that here is the aircraft and then the wingspan. So, depending upon how we place the wing and then how it is oriented and the length component if you reduce, then the pressure drag can be reduced. So, say like this say various measures we can adopt to reduce the pressure drag. And second kind of drag, the friction drag, we can reduce the friction drag by making the surface smooth So, the one of the step which you can adopt to reduce the friction drag is say the surface is rough, make it more smooth, and also the flow should be laminar for the greater portion of the body. If the flow is laminar, then the friction drag effect will be much lesser compared to the turbulent flow effects. So, flow should be laminar for the greater portion of the body. So, these are the two measures possible with respect to the friction drag to reduce the friction drag. So, now we have seen say with respect to the pressure drag, if we make the body streamlined, then the pressure drag is reduced. So, that we have already seen here, make the body streamlined. So, let us see we will discuss here briefly about the streamlined body. So, a body is said to be streamlined if its shape is such that separation occurs towards the rearmost part of the body. So, say we call a body as streamlined if the shape of the body is such a way that the boundaryless separation occurs towards the rearmost part of the body. So, in that case you can see that the wake formation is very small. So, and it offers least possible resistance to the flow of air, water or other fluids where the body is immersed. So, say we can see say the airfoil which we have already discussed earlier, airfoil or the fish. So, you can see that the shape of the fish is in such a way that it is, we can say that the body is streamlined. So, that the wake formation is very small, and then the shape is such a way that when the fish moves, the separation occurs towards the rearmost part of the body. So, here you can see that whenever the airfoil is placed like this, you can see the flow is coming like this, and then the wake formation is only due to the placement in such a way that, and also the body, say the airfoil is streamlined, so that here the wake is very small, and then the drag effect will be much less, especially the pressure drag effect will be much smaller. So, similarly the fish, the case of a fish also, we have seen the shape of the fish is in such a way that we can say that the wake formation is very small, and the separation, the boundaryless separation occurs towards the rearmost part of the body of the fish. So, and the same airfoil, if you place it in the other way, as we have seen, say the airfoil is concerned, if it is how we are placing it also important, what is the angle of attack, accordingly the drag effect changes. So, this is about the streamlined body, and then the next kind of body which we have seen is so called bluff body. So, the case of bluff body, say as in the case of a sphere or the case of a circular cylinder, you can see that the body shape is such that separation occurs much ahead of the rearmost part of the body. So, you can see that this is the sphere here. So, the separation occurs much ahead of the rearmost part of the body. So, that is why it is called as a bluff body, and then you can see the wake formation is large as in the case of a sphere or a cylinder kind object as shown in this figure. So, the bodies, as far as with respect to the drag is concerned, we can say to reduce the drag effect, we can say that we should have a streamlined body. So, either the body, say streamlined body or bluff body is concerned, you can see the wake formation will be much larger, and then the pressure drag effect will be much more. So, if you consider the drag on streamlined and bluff body, so here you can see that if you consider circular cylinder like this is the blunt body or the bluff body. So, you can see that the separated flow is here. So, here the pressure drag in the case of the bluff body, the pressure drag will be much higher. So, here in this figure the friction drag is shown as red color, and the pressure drag is indicated as the yellow color. So, you can see that in the case of a bluff body, like in the case of a circular cylinder, the pressure drag will be much more, and then friction drag or skin friction drag will be much smaller, and also the total drag will be much higher compared to the streamlined body. So, as we saw the case of an airfoil which is a streamlined body, you can see that the skin friction drag, since here you can see that the skin friction drag will be more compared to the pressure drag. So, the pressure drag here is also indicated as yellow color, and the skin friction drag is shown as red. So, you can see that the relative drag force will be much smaller for a streamlined body as shown in this figure. So, here the friction drag is lower than the pressure drag in the case of bluff body. So, for bluff body the friction drag is smaller and the pressure drag is more, and then in the case of a streamlined body the friction drag is higher and then the pressure drag is much smaller. So, these are the effect with respect to whether the body is a bluff body or whether the body is a streamlined body. So, accordingly we can say that the drag effect is the pressure drag or the friction drag, which one is more in the case whether it is a bluff body or it is a streamlined body. So, the drag effect is concerned this pressure drag and the friction drag are the two most important effect or the drag is concerned. Other than this pressure drag and the friction drag, there can be also some other kinds of drag. So, depending upon, say for example, if you consider in this slide the movement of a boat. So, here a boat is going through the water where also the wave effects are there, and then there are so many other kinds of drags are also possible. So, except pressure and friction drag, there are different kinds of drag. So, these are, first one is called induced drag, and second one is called profile drag, and third one is called heel drag, and fourth one is called residuary drag, and fifth one is called added wave drag. So, if you consider the movement of a boat, then you can see that many of these drag effects will be coming over the boat which is moving over the water like this. So, but most of the time the pressure drag and the friction drag are the most important components of the drag force, but others are also possible like induced or profile drag or the heel drag like that. So, let us see the definition of this induced or this various kinds of other drags. So, now the induced drag, this induced drag actually it is the drag force induced in the body due to the lift forces acting on it. So, we have seen when a body is immersed in the fluid, either in the moving fluid or depending upon whether the body is moving or the fluid is moving. So, with respect to the say the immersed body, we have the drag and as well as lift. So, this lift component also may induce some kinds of drag, that is called induced drag. So, here you can see that if you consider an airfoil like in this figure here, then you can see that the drag force will be in this direction and then the lift force will be in the normal direction, upward direction. Then you can see that since the airfoil is placed with respect to some angle of the with respect to the free stream flow, then you can see that an induced drag will be coming here. So, this is due to the lift force. So, if there is no lift force, then there is no induced drag. So, as in the case of airfoil, you can see that when the angle of attack increases, the induced drag also increases. So, actually this induced drag is concerned, and this depends upon how we are placing the body or how its profile is there, and how you say place the body with respect to the flow direction of the fluid. So, this is so called induced drag. And then next one is the profile drag. So, this profile drag is developed if the, say for example, if we consider the airfoil, if it is infinitely long, then the flow to be 2 dimensions. So, this is coming from the profile of the body. So, that is why it is called a profile drag. So, this depends on the shape or profile of the, say if we consider the airfoil, it depends upon the shape and how you say place it or the profile. So, that is called a profile drag. And then third kind of drag here is called the heel drag. So, this heel drag, this is due to the change in drag, sometimes say negative. So, this occurs due to the change in the hull shape of a boat below the surface. So, we have seen this boat movement here. So, if the hull shape, depending upon the hull shape of the boat, then you can see that there is a possibility of the say there is just a change in the drag effect, and this occurs due to the shape, which shape you give, say in the case of a below the surface, for a boat below the surface, how it is provided and then how it is moving. So, that is called the heel drag. And then the next kind of drag is called residuary drag. So, this is actually the combination of the, so we have seen that when the boat is moving, there is also waves will be there on the water surface, and then say how these waves behave with respect to the movement of the boat. So, this residuary drag is coming, it is actually the combination of the wave making and the viscous pressure drag or the foam drag. So, this is the resistance caused by the creation of bow and stern waves, as in the you can see that here in this figure. So, when this boat is moving, so how it behaves and how the waves are coming. So, with respect to the drag formation, that drag is called residuary drag, and also then added wave drag, this is the additional drag caused by the oncoming waves. So, these are some of the other kinds of drag than the pressure drag or the friction drag, which we consider, which are the most important kinds of drag for the fluid immersed in a body or the body moving through fluid. So, now we have seen various kinds of drag here. So, let us see how this drag effect will be there with respect to, say, a boat moving through, say, through the sea or a lake. So, what kind of, say, how these various kinds of drag effects will be coming over the boat. So, here this slide shows, say, with respect to the speed of the boat, the drag is also plotted here. So, you can see that this figure shows the contribution of different drag forces. So, here this line shows the total drag. So, you can see that this friction drag is, which is also predominant here, this is the friction drag, and then we have this residuary drag, and then this heel drag is very small, and then we have this blue color here, this color here induced drag, and then added wave drag. So, that the total drag is this line is the total drag, and then also you can see that this depends upon the speed of the boat. With respect the speed of the boat is increasing, you can see that the drag effect also is also increasing as plotted here. So, the various kinds of drag here we have seen, and then say with respect to the movement of a boat, how the drag variations for with respect to various components. So, that is what is explained here in this slide. So, now we have seen various kinds of drag and how the drag can be reduced with respect to the shape or with respect to the placement of the body in the fluid. So, now we will analyze how we can calculate, we can find this drag coefficient, or how to find out the drag and lift with respect to the fluid flow, and then with respect to the body which we consider. So, as we have already defined the drag force, say we have already seen the equation for drag force and lift force. So, if you analyze the, say, whenever we consider any body immersed in fluid, so with respect to the drag effect and lift effect, if you consider a dimensional analysis, and say we can see that with respect to the various parameters which have to be considered while dealing with the drag force are the length of the body. So, the length dimensions, length, breadth, and other, see the depth or these dimensions, and then rho the density of the fluid, and mu is the coefficient of dynamic viscosity, and E is the elasticity or the elastic force or the elasticity with respect to the fluid, and G is the acceleration due to gravity, and then the free stream velocity u infinity. So, these are the important parameters we have to consider while analyzing the drag force and the lift force. So, similarly, so for the drag force can be considered as a function of this length L, the density rho, the coefficient of viscosity mu, and the elasticity E, and acceleration due to gravity, and the free stream velocity. So, similarly, the lift force also can be considered as a function of these parameters as shown here. FL is equal to F2 as a function of L, rho, mu, E, G, and u infinity. So, we can do an analysis with respect to these various parameters. So, using the dimensional analysis, we can show that, especially while doing experiments, we will be doing the dimensional analysis. So, through dimensional analysis, we can show that this drag force and then lift force, say If we consider Fd, the drag force Fd divided by rho L square u infinity square, where u infinity is the free stream velocity. So, that is equal to, as a function of say F3 here, rho u infinity L by mu, u infinity square by Lg, u infinity by square root of E by rho. So, this similarly this lift force we can write as Fl divided by rho L square, u infinity square is equal to, as a function of F4, rho u infinity L by mu, u infinity square by Lg, u infinity by square root of E by rho. So, we can represent in the dimension analysis like this with respect to the drag force and then with respect to the lift force. So, after writing like this, we can see that. So, we have seen that this coefficient of drag and coefficient of lift we can write in terms of this. So, the coefficient of drag is equal to the drag force Fd divided by half rho u infinity square into A, where A is the area of the body which we consider. So, where u infinity is the free stream velocity. Similarly, coefficient of lift we can write as Cl is equal to the lift force Fl divided by half rho u infinity square A. So, now if we consider this with respect to the analysis here, the dimension analysis which is explained here in this slide, we can write this coefficient of drag can be put as a function of the Reynolds number, Froude number and Mach number. So, you can see that this component here rho infinity L by mu represent the Reynolds number, and the second term u infinity square by Lg that represent the Froude number, and this u infinity by square root of E by rho represent the Mach number. So, that we can represent the coefficient of drag and the coefficient of lift in terms of the as a function of the Reynolds number, Froude number and the Mach number. Generally, say when we consider the drag and lift effect, and then when we are finding the coefficient of drag and coefficient of lift, we can show that this Froude number and Mach number, that term or that effect will be much smaller. So, we can neglect it, and generally we can represent this CD coefficient of drag as a function of Reynolds number and also coefficient of lift as a function of Reynolds number by neglecting this Froude number and Mach number which we considered here in this analysis. So, this way we can represent the coefficient of drag and coefficient of lift. So, now we will analyze the drag effect, say initially with respect to the small Reynolds number, and then we will see the laminar flow with especially with respect to a flat plate. We will see the drag force for the coefficient of drag and its various parameters, coefficient of drag and other parameters for flat plate. So, initially let us discuss about the drag at small Reynolds number. So, this Stokes conducted a number of experiments with respect to the drag effect, and then say especially in the case of Reynolds number is small Reynolds number, say especially when Reynolds number is less than 1. So, this category of flow has been classified as creeping flow, which we discussed earlier. So, here you can see that the drag is proportional to the, so through experiments Stokes showed that the drag is proportional to the free stream velocity u infinity. So, if we consider as in this figure, say if we consider a sphere, the creeping flow, so wherever the Reynolds number is very small, so that flow which is categorized as creeping flow. So, you can see that here the free stream is coming here, and then if we consider a sphere like this, the creeping flow over a sphere, say the radius r, and if we consider an angle theta like this. So, here the number of experiments conducted by Stokes, and then he has shown that the deformation drag for a creeping flow wherever the Reynolds number is very small, as we have seen here, say Reynolds number less than 1. So, there Stokes showed that this deformation drag Fd is equal to 3 pi mu u infinity into d. So, where mu is the dynamic coefficient of viscosity, u infinity is the free stream velocity, and d is the diameter of the sphere as shown here. This is the diameter of the sphere, so and u infinity is the free stream velocity. So, for small Reynolds number considered the creeping flow, Stokes showed that this deformation drag Fd is equal to 3 pi mu u infinity to d. So, this is known as Stokes flow. This where this equation is applicable, that kind of flow is called a Stokes flow. And as far as drag is concerned, Stokes showed that generally this out of the total drag, 2/3 is the, say in the case of a creeping flow, say if we consider the creeping flow over a sphere, he showed that 2/3 is friction drag and 1/3 is generally a pressure drag. So, this is the case where the Reynolds number is so small, say generally less than 1. So, there Stokes showed this drag effect is concerned, 2/3 will be generally the friction drag and 1/3 is the pressure drag. And also say if we consider the Stokes flow around a sphere, then the coefficient of drag, we can show that the coefficient of drag is equal to 24 mu divided by rho u infinity d, d is the diameter of the sphere. So, that is equal to 24 by R e. So, this is valid for Reynolds number less than 0.1, and when the Reynolds number is between 0.1 to 1, we can show that this coefficient of drag will be 24 by R e into 1 plus 3 by 16 into R e, where R e is the Reynolds number which we consider. And again say a large number of experiments conducted for different Reynolds number, and this coefficient of drag we can show that it will be C d is equal to 24 by R e into 1 plus 3 by 16 R e to the power 1 by 3 for Reynolds number up to 100. So, this you can see that the coefficient of drag is varying with respect to the Reynolds number as shown in this slide. So, this creeping flow which we discussed earlier also with respect to the Stokes flow. So, these kinds of analysis is very important, especially in civil engineering, where sedimentation and silting problem is there in water, and also the settlement of dust in the atmosphere. We can utilize this Stokes flow, and then with respect to the we can calculate the coefficient of drag and also the drag force coming on the particle. So, that is the case where the Reynolds number is so small, where we consider the as a creeping flow. So, we have seen the drag effect, the coefficient of drag, and then the drag force. So, now we will further analyze here the drag effect, coefficient of drag, and various other parameters with respect to the flow over a flat plate. So, we will consider, we have already seen this flow over a flat plate case. So, when we consider the flow over a flat plate, there can be 3 conditions. First one is the boundary layer formation, is that is a laminar boundary layer, and then there is a transition stage, and then there can be turbulence zone. So, if we consider the drag over a flat plate, so you can see that generally there is no variation in pressure in the flow direction as we have discussed earlier. So, that velocity gradient is constant. So, in this case you can see that here we have the laminar zone, and then there is transition zone, and here with respect to boundary layer formation we have the turbulence zone. So, now with respect to these various cases, we will determine the drag, how to find out the drag for a laminar case, and then turbulent case, and also the transition case. So, when we consider, as we discussed for drag over a flat plate, boundary layer is fully laminar. So, generally it happens when the length of the plate is short, or initially, as we have seen the previous slide, initially it can be laminar and then transition and then turbulent, or say only laminar boundary layer if the length of the plate is very small, and then the velocity is also the free stream velocity is small. And then boundary layer, second case is when the boundary layer is fully turbulent. So, it develops after certain distance along the plate, as we have seen here. So, here finally here the boundary layer is totally turbulent. And then the third case is boundary layer in transition from laminar to turbulent. So, this is the case where the transition zone, here you can see that this is a laminar, here it is turbulent. So, here is the transition zone. So, here we want to find out the drag force with respect to, say, for the flow of a flat plate, since this is one of the generally used typical case to analyze various parameters. So, here also to analyze the drag force, the coefficient of drag, we use the flat plate, flow over a flat plate problem. So, now first let us consider the laminar boundary layer formation, or the flow over for a flow over a flat plate if the flow is fully laminar boundary layer, and then how we can get the drag coefficient and then the drag force. So, this flow with respect to the flow of a flat plate for fully laminar boundary layer, Prandtl analyzed this problem by using the Prandtl's boundary layer equations, which we have discussed earlier. So, you can see that here this is the flat plate here, and then flow free stream velocity is coming like this, and then we have the boundary layer formation. So, this is the boundary layer thickness, and here the u infinity is the free stream velocity. So, by considering the Prandtl boundary layer equations, from the law of similarity we can write, say, the velocity at any location u by u infinity is a function of yx nu and u infinity, where nu is the kinematic viscosity here. So, this is equal to f eta. So, where eta we can represent as this y is in this direction. So, eta is equal to y by delta, the location which we consider where the velocity is u and the location is at y. So, now with respect to this, say, from the boundary layer flow analysis of unsteady motion, Prandtl analysis showed that this boundary layer is proportional to square root of nu into T, where nu is the kinematic viscosity and T is the time required for a fluid particle to travel a distance x with velocity u infinity. So, here you can see this figure earlier. So, the flow is taking place like this, and then we have this the fully laminar boundary layer. So, delta, the boundary layer thickness, is proportional to square root of nu into T, where T is the time required for a fluid particle to travel a distance x with velocity u infinity, the free stream velocity. So, this we can write, this is proportional to square root of nu x by u infinity, or we can write delta is equal to x by square root of r x, where this r x is the Reynolds number at that particular location where we consider. So, now in the previous slide we have seen this y is represented as this eta is equal to y by delta. So, this is equal to y into square root of u infinity by nu into x. So, with respect to this equation here, Prandtl analysis showed that eta is equal to y into square root of u infinity by nu into x. So, here if you introduce the stream function, which is defined as psi is equal to integral u dy. So, that is equal to u infinity delta integral f eta d eta. So, that is equal to u infinity. If we substitute for delta, we can write u infinity is into square root of nu x by u infinity into function of f eta d eta. So, that we can write psi is equal to the stream function psi is equal to square root of u infinity into nu into x the f eta, where f eta is equal to integral f eta coming from here f eta d eta. So, now we know that the velocity can be represented as u is equal to del psi by del y. So, that we can write u is equal to del psi by del eta into del eta by del y. So, this is equal to u infinity f dash eta. So, velocity is represented as at any location u is equal to u infinity f dash eta, and then the velocity gradient we can write as del u by del y is equal to del u by del eta into del eta by del y. So, this is equal to u infinity square root of u infinity by nu x into f double dash eta. So, second derivative this f dash f eta. So, here first derivative, so here the second derivative f double dash eta, and then the shear stress on the surface of the flat plate from the Newton's law we can write tau is equal to mu du by dy at y is equal to 0. So, that is equal to mu u infinity square root of u infinity by nu x f double dash at 0 location. So, the shear stress on the surface of the flat plate, and then by using this Prandtl's equations, Blasius derived the solution by the discussed steps, and then the Blasius solution for the boundary layer flow analysis over a flat plate at eta is equal to 0. He showed that f double dash 0 is equal to 0.332. So, that we can write, say, from the velocity profile obtained by Blasius solution, the boundary layer thickness delta is equal to phi into x by square root of r x, where r x is the Reynolds number at that particular location which we consider at, say, where u by u infinity is equal to 0.992 with respect to the definition. So, that delta is obtained as phi into x by square root of r x, where r x is the Reynolds number, and also this here delta star, the displacement thickness is equal to 1.73 x, and Blasius showed that delta star is equal to 1.73 x divided by square root of r x, where Rx is the Reynolds number at that particular location, and the momentum thickness theta is equal to 0.664 into x by square root of Rx, where Rx is the Reynolds number at that location. So, now from the equation number 1 here, we substitute in this equation number 1, we can show that tau 0 is equal to 0.332 mu u infinity square root of rho u infinity by mu x. So, that is equal to 0.332 rho u infinity square by square root of Rx, where Rx is the local Reynolds number represented as rho u infinity into x by mu. So, this way, by using the Prandtl's equations, Laplace derived this expression for delta, delta star, theta, and then also he got expression for tau 0, the shear stress on the flat plate. And then now we want to see with respect to the drag effect. So, when we consider the local friction drag coefficient with respect to this figure here, local means at that particular location. So, here Cf is equal to the local friction drag coefficient, Cf is equal to friction drag divided by dynamic pressure drag. So, that we can write Cf is equal to the friction drag is given as tau 0 into A by this dynamic pressure drag is obtained as half rho u infinity square into A. So, this is equal to tau 0 by half rho u infinity square. So, this he showed with respect to the previous expressions here for tau 0, which is obtained here. So, Blasius showed that the Cf is equal to 0.664 by square root of Rx, where Rx is the local Reynolds number. So, this Cf is the local friction drag coefficient for the laminar boundary layer formation over a flat plate. So, now the friction drag, say over one side of the plate of length L per unit width, we can write as f df is equal to integral 0 to L tau 0 dx. So, this is equal to integral 0 to L 0.332 divided by u infinity square root of u infinity x by nu into rho u infinity square dx. So, this is equal to 0.664 rho u infinity square into square root of nu L by u infinity. So, this is the friction drag, and then from this f df, the friction drag over one side of the plate. So, the average coefficient of friction drag we can get from this expression, the Cf is equal to f df by half rho u infinity square into L. So, this is equal to 664 u infinity square root of nu L by u infinity by half rho u infinity square into L. So, that is equal to 1.328 divided by square root of RL, where RL is the Reynolds number at the trailing edge of the flat plate. So, finally, here we got the coefficient of friction drag for the plate CFS as Cf is equal to 1.328 divided by square root of RL. So, in the previous case here what we considered here is the local friction drag coefficient, which we got as 0.664 divided by square root of Rx. So, here we got as Cf is equal to 1.328 divided by square root of RL, where RL is the Reynolds number at the end of the plate which we consider. So, now like this here various parameters have been derived for the coefficient of drag, whether it is local or at the end of the plate. So, with respect to this we have seen, say, by starting from the Prandtl boundary layer equations, the parameters like delta, delta star, and then momentum thickness, etc., derived by Blasius in the earlier slides which we have discussed now. So, now we will discuss, say, a small example here. So, the example here is, say, we have to calculate the friction drag on a flat plate. So, here this is a flat plate problem. So, calculate the friction drag on a flat plate of 25 centimeter wide and 60 centimeter long, placed longitudinally in a stream of oil of relative density 0.945 and kinematic viscosity 0.8 Stokes, flowing with a free stream velocity of 3 meter per second, and also find the thickness of the boundary layer and the shear stress at the trailing edge. So, here the problem is, this is the free stream velocity, we have free stream velocity of 3 meter per second, and then the relative density of the fluid is 0.945 and length of the plate is 60 centimeter and width is 25 centimeter and the kinematic viscosity is 0.8 stokes. So, this is the section of the plate. So, for this problem we have to find out the thickness of the boundary layer and the shear stress at the trailing edge. So, we have already seen for this kinds of problem. Now, for the we can first find out the at the trailing edge what will be the Reynolds number, so that we can see that with respect to the whether the flow is laminar or not, and then we can use the equations which we have discussed earlier to get the boundary layer thickness and the shear stress. So, here for this problem the Reynolds number at the trailing edge R is equal to REL is equal to UL by nu. So, 3 into 0.6 by 0.8 into 10 to the power minus 4, since here 0.8 stokes is the kinematic viscosity. So, this is equal to 2.25 into 10 to the power 4. So, Reynolds number at the trailing edge of the plate is 2.25 into 10 to the power 4. So, here you can see that 1 stoke is equal to 10 to the power minus 4 meters square per second. So, here say we have when we discussed the initially about the boundary layer, we have seen say the especially for the case of for flow over a flat plate, when the Reynolds number is less than 5 into 10 to the power 5, we have categorized the boundary layer as laminar. So, here we got 2.25 into 10 to the power 4 as Reynolds number. So, you can see that the boundary layer is laminar. So, we can use the equations which we have seen earlier, since the boundary layer is laminar in nature. So, the Blasius solution we can use. So, delta is equal to 5 into x by square root of r x, that is the boundary layer thickness equation given by Blasius. So, at the trailing edge means at the end of the plate. So, here at this location, so that means the boundary layer thickness here. So, you can see that L is equal to 0.6. So, delta L is equal to 5 into 0.6 divided by Reynolds number square root of 2.25 into 10 to the power 4, which is the Reynolds number. So, we get the boundary layer thickness at the trailing edge as 0.02 meter. And now, the second problem here is to find out the shear stress at the trailing edge. So, to find out the shear stress, we have already seen this equation here. So, this equation is here tau L is equal to half rho infinity square CFL. So, that is equal to half rho u infinity square. So, here the CFL we have already seen 0.664 in the square root of REL. So, this is equal to rho is 0.945 into 1000 into say free stream velocity is 3. So, 3 square into 0.664 divided by 2 into square root of 2.25 into 10 to the power 4. So, this will give the shear stress at the trailing edge as 18.82 Newton per meter square. And then the drag on one side of the plate FD is equal to CDF into LB, L into B into rho infinity square by 2, and then the CDF, that means the when we consider say here the say total drag. So, we have seen the drag is concerned, the local drag coefficient is concerned local drag coefficient as well as the full drag coefficient, as we have seen here the average coefficient of friction drag CDF here 1.328 root RL. So, this equation we can utilize here. So, that CDF is equal to 1.328 divided by square root of REL. So, that is equal to 1.328 divided by square root of 2.25 into 10 to the power 4. So, this gives CDF is equal to 8.85 into 10 to the power minus 3. And then the force due to drag we can calculate FD is equal to CDF into area L into B into rho u infinity square by 2. So, this is equal to 8.85 into 10 to the power minus 3, which is the CDF into 0.6, L is 0.6 and B is 0.25 here into 0.945. So, here B is 25 centimeters. So, that is by 0.25 into 0.945 into 1000 into 3 square by 2. So, this gives 5.695 Newton. So, total drag force on both sides of the plate is equal to say here this calculation is for one side. So, both sides it will be 2 times the drag force calculated. So, 2 into 5.695 is equal, that gives 11.29 Newton. So, like this we can solve the drag force with respect to the laminar boundary layer formation in the case of a flat plate. And now, the next case is drag over flat plate where the boundary layer is turbulent. So, we have seen, so now the laminar zone we have seen. Now, if the boundary layer is fully turbulent, then say the various equations here we will consider for turbulent boundary layer. So, now here say we have seen when we discussed the boundary layer earlier. So, we have seen the momentum integral equation. So, with respect to this, for fully developed turbulent boundary layer, we can see over a flat plate the momentum integral equation may be written in slightly different form as d by dx of integral 0 to delta u into u infinity minus u dy, so that is equal to tau 0 by rho as in equation number 1. So, where u infinity is the free stream velocity and u is the velocity at any location, tau 0 is the boundary shear stress and rho is the density. And then Prandtl experimentally showed that for turbulent boundary layer, we can write this u by u infinity is equal to y by delta to the power 1 by 7. So, this is coming from the experimental observation by Prandtl. So, this is u by u infinity is equal to y by delta to the power 1 by 7 as in equation number 2. This is known as Blasius 1/7 power law. So, this is through experimental observations. And then also the velocity distribution turbulent flow over a flat plate, say when the Reynolds number is less than 10 to the power 7, through experiments it has been shown that u by square root of tau 0 by rho is equal to 8.74 into square root of tau 0 by rho into y by nu to the power 1 by 7th. And also here this say with respect to the Blasius analysis and using the momentum equations, say with respect to the pipe flow, for turbulent flow in pipes, it is shown that tau 0 is equal to 0.034 rho v square v d by nu to the power minus 1 by 4 as given in equation number 3, and the average velocity for with respect to pipe flow, we can show that v is equal to 0.817 the maximum velocity u max. So, here the maximum velocity is the free stream velocity. So, that is equal to 0.817 u infinity. So, by using this here we can show that tau 0 is equal to 0.0233 rho u infinity square u infinity delta by nu to the power minus 1 by 4 as in equation number 4. So, now if you use the previous equation number 1 and then equation number 2 here and then equation number 4, we can show that delta by x is equal to, for turbulent boundary layer, delta by x is equal to 0.379 divided by r x to the power 1 by 5 as given in equation number 5. So, this is to find out the boundary layer at any location with respect to the turbulent boundary layer formation. And now, if you use this equation number 5 and 4 together, we can show that tau 0 is equal to 0.0295 rho u infinity square r x to the power minus 1 by 5 as given in equation number 6. So, now for turbulent boundary layer local friction coefficients, we can find out Cf is equal to tau 0 by half rho u infinity square as we have discussed earlier. So, this for turbulent boundary layer, the local friction coefficient we can show that Cf is equal to 0.059 divided by r x to the power 1 by 5, where r x is the Reynolds number, local Reynolds number as in equation number 7. And the friction drag per unit width for one side of the plate is, we can integrate f df is equal to integral 0 to L tau 0 dx. So, this is equal to 0.0368 L rho u infinity square r l to the power minus 1 by 5, and then and hence Cf is equal to f df by half rho u infinity square L. So, this is we can show that Cf is equal to 0.074 divided by r l to the power 1 by 5 as given in equation number 8. So, this equation number 8 through experiments shows that this equation number 8 is valid for Reynolds number in the range of 5 into 10 to the power 5 and between 10 to the power 7 Reynolds number, 5 into 10 to the power 5 to 10 to the power 7. And when again Prandtl calculated and also shown through experiments that when the Reynolds number is greater than 10 to the power 7, he showed that the friction coefficient Cf is equal to 0.455 divided by log 10 r l to the power 2.58. So, this is shown by Prandtl and verified through experiments as shown this equation 9. So, this gives for turbulent boundary layer, this gives the various equation friction coefficients and the coefficients say the average friction drag coefficients for the turbulent boundary layer. So, next say we will be discussing further on the drag force and the drag coefficients in the transition case, and also further with respect to various shapes and with respect to various body parts how the drag coefficient changes we will be discussing in the next lecture.